Welcome to the deep dive.
Okay, so we've got some really interesting material here today, all about numbers.
Mm-hmm.
And we're not going for like dry textbook stuff. We want to cut right to the chase based on what you shared about this big split, rational versus irrational numbers.
Yeah, it's a fundamental split, really foundational in math.
Our mission here is to kind of see what really makes them tick, what's different, especially, when you look at their decimals. The source has some great insights there.
It really does. It's like dividing the number world in two. The material's a good map for that.
Okay, so let's dive in. The source material starts with this big umbrella term, real numbers. That's basically everything we usually think of as numbers.
Right. And under that umbrella, just two main types. That's the first key thing. Rational numbers and irrational numbers.
Okay, rationals first. The source makes it super clear. These are numbers you can write as a simple fraction, a over b.
Exactly. Where a and b are integers, whole numbers, and crucially, b isn't zero. You can't divide by zero. So things like, I don't know, -8 or 0 itself or 6/58, 29ths. The source lists examples like these. They're all rational. Even says every integer, every normal decimal number.
And the really useful bit from the source is how to spot them using decimals. It links straight back to that ab thing.
How so?
Well, if it can be written as a fraction ab, its decimal has to do one of two things. It either stops, terminates.
Like 18 is just 0.125. Boom, done.
Exactly. Or it goes on forever, but,
Yeah.
and this is the key, it has a repeating pattern.
Ah, right. The source showed 49 is 0.4444. Just 4 is forever.
Or 1130 was 0.3666 with the sixes repeating.
Okay. That pattern is the dead giveaway.
It's the signature, yeah. The source is clear on that. Comes from the math of dividing integers. Eventually, the remainders have to cycle.
predictable.
Okay, predictable decimals for rationals. But then
Huh,
the other side. This is where my brain starts to hurt a bit.
yeah, the irrationals.
The material says these are the ones you cannot write as that simple ebb fraction. Correct. And because of that, their decimals are completely different. The source points this out very clearly.
How are they different then?
They also go on forever, so they're non-terminating.
Okay.
But they never repeat. No pattern, ever.
Wait.
The digits just keep coming, randomly, it seems.
Wow, okay. Non-terminating and non-repeating.
That's the definition for irrationals based on their decimal form.
And the source gives examples like square roots of numbers that aren't perfect squares, like root 2.
Exactly. Square root of 2, square root of 5, cube root of 10, things like that. The source even shows the long division for root 2. You can see it just keeps going. No pattern emerges.
And pi. Of course, pi.
Famous example. The material mentions we often use 227, which is rational,
Right, because it's a fraction.
but it's just an approximation. The real pi, its decimal expansion is endless and never settles into a repeating block. That's why pi is irrational.
It feels fundamentally different, doesn't it? These endless, patternless numbers.
It really does.
The source also mentioned surds. Is that just another noun for irrationals?
Not quite. It's a specific type of irrational. The source defines surds as basically roots of rational numbers that turn out to be irrational.
Like square root of 3 or cube root of 6, like you said.
Precisely. So all surds are irrational, but not all irrationals are surds.
Ah, because pi isn't a root of a rational number.
Exactly. So pi is irrational, but it's not a surd. It's a subtle distinction the source makes.
Okay, and this leads to that technique, rationalization.
Yeah, particularly rationalizing the denominator. It's a practical tool highlighted in the material. Sometimes having a square root, an irrational number, and the bottom of a fraction is awkward.
Like 1 over root 2?
Rationalization is just a way to rewrite it so the bottom number is rational. You multiply the top and bottom by root 2 in that case.
And you get root 2 over 2. The bottom is now rational.
Right. It's just a technique, but it comes directly from understanding these number types.
So pulling it all together for you, the listener, but based on this material, the big split hinges on that fraction test. Ab, can it be done or not?
And that directly tells you about the decimal. Rationals. Terminator, repeat. Irrationals. Non-terminating, non-repeating.
That seems like the core takeaway from this source material.
Yeah, and the material gives loads of examples and ways to, spot them and work with them.
We've just scratched the surface here, really, guided by your research. But here's something maybe to think about on your own. Given that irrational numbers have these infinite, non-repeating decimals, while rationals are sort of tamer, more predictable, does that suggest anything about maybe how many of each type there might be? Are there more rationals, or could there actually be, surprisingly, more irrationals out there?